Hello, my name is Dan Brunner, and in this video, I'll be going over how to solve problem 3.115 from Chapter 3 of the Fundamentals of Mass and Heat Transfer textbook. This is actually a problem that I did back when I took Heat Transfer 1, and so I wanted to try it again and see how much I could do without looking back at my old notes. And I will say that the first part of the question, which involves finding the rate of heat generation of a computer chip, when there are no fins is relatively straightforward. But the second part, which involves fins, is a little bit more tricky and requires some more assumptions. So let's get into it. Um, Looking at the problem statement, we can see that we have a computer chip, and attached to this computer chip is a silicon carbide layer surrounding the entire chip. And attached to this layer, if we're looking at the second part of the question, there are these nano wires also made out of silicon carbide with a diameter of 15 nanometers. And so this is an extremely small scale. Um, and we're trying to find the maximum rate of heat generation um, that's allowed if the temperature of the computer chip must remain less than 85 degrees Celsius. So again, we'll be looking at this scenario without fins, and then again with fins, and we'll see how different those answers are. So what are we given? We're given that the diameter of each fin is 15 times, well, sorry, 15 nanometers. It's a little bit more clear. The area of the computer chip is 10 microns by 10 microns. So a total of 100 picometers, or sorry, 100 times 10 to the negative 12th square meters. Ignore the picometers, that was incorrect. Um, our ambient temperature is 293 Kelvin. We have a convection coefficient of 1 times 10 to the fifth watts per meter squared Kelvin. The length of each fin is 300 nanometers. And we have these fins creating this array that consists of 40,000 fins. The maximum allowable rate of heat generation must be such that the temperature of the computer chip remains less than 85 degrees Celsius or 358 Kelvin. And last but not least, we're given that the thickness of the silicon carbide layer that encapsulates the computer chip has a thickness of or sorry, that thickness value is 100 nanometers. And an important thing to note is that we're not given the thermal conductivity of silicon carbide. Um, and sorry, that right here is supposed to say carbide, not carbine. Um, and so we'll have to look that up. The solution for this problem uses a value from the tables in the textbook. However, I just looked up the average thermal conductivity of silicon carbide, and I got a value of 305. Um, so we'll see how that number affects our results, and if the results that I get when I go through and solve this problem are the same as the solution results. Again, we're asked to find the maximum allowable rate of heat generation for an unfinned and then a finned scenario. So what assumptions are we going to make to help us calculate this maximum allowable rate of heat generation? Well, we're going to neglect any radiation, so we're essentially assuming that there's negligible net radiation heat transfer. We're going to assume that our conditions have reached a steady state, meaning that no variables are time varying. Any time derivatives will automatically go to zero. We're going to assume that we have 1D conduction through the silicon carbide. And again, I'm assuming that that conductivity of the silicon carbide is 305 watts per meter Kelvin. We're going to assume that the silicon carbide has constant and isotropic properties, meaning that the um, thermal conductivity does not change over time, and it is the same regardless of which direction you go in. We're going to assume that we have uniform and constant convection over the surface of the computer chip silicon carbide layer, or the thin surfaces themselves. We're going to assume these last two assumptions are probably the most important, or the most consequential for when we're solving this problem. We're going to assume that the fins have adiabatic tips and that the fins themselves have uniform circular cross sections. So basically, they're just cylindrical fins. And the adiabatic tip assumption is basically us saying that the length of the fins is much larger than the thickness or the diameter of the fins. So the heat transfer that's going through, that's conducting through the fin, all of that heat is essentially taken away through convection before a substantial or a significant amount of heat can reach the tip. And so any heat transfer that does leave the tip is considered negligible. For our governing equations, we're going to use the thermal resistances for conduction and convection. We'll have to derive the thermal resistance for the fin, which we'll get to later. And well, actually, we can get to it right now. The heat transfer rate through the fins is equal to this equation right here, where the number of fins is multiplied by the fin efficiency times the convection coefficient times the area that the fins take up times this theta b term. And this entire equation is about equal to the change in temperature over the thermal resistance of the fins. And so if we want to find the thermal resistance of the fins, we can simply look at this equation right here. And we can say 1 over what expression will give us the resistance of the fins. Well, if this theta b term is about equal to the change in temperature, then our fin resistance will be 1 over the number of fins times the efficiency times the convection coefficient, and finally times the fin area, all in the denominator. The major governing equation that we'll also be using is the first law of thermodynamics. We'll be conducting a closed system energy balance using the first law. And a few other equations we have here. We have the characteristic length for a cylinder is going to be about equal to the length of the cylinder plus a quarter times the diameter of the cylinder. And what the characteristic length basically is just a quantity that establishes the scale of the system. So it's comprised of, it's composed of the dimensions that are most significant when determining the scale of the system. And our final governing equation, which will help us to simplify some things when we're going through the analysis, is that our fin area is about equal to the perimeter around the fin cross section times the characteristic length. So let's look at the first part where we have an unfinned computer chip. So we still have the layer of silicon carbide surrounding the computer chip, but we don't have any fins on either side. And one important thing to note is that I don't have it drawn in this picture here. Actually, it's right here. So we have fins on both sides of the computer chip. We also have the silicon carbide layer on both sides. So we'll have to account for that heat transfer through either side. And so going back to the first part where we have an unfinned system, we can create a thermal circuit, which is composed of the thermal resistance, the conductivity thermal resistance, and the convection thermal resistance. And since these resistors are aligned in series, we can simply just add them together. And so then if we substitute in our expressions for each of those thermal resistances, we can get this final expression for the total resistance. Uh, Performing a closed system energy balance on the first law of using the first law of thermodynamics, we can then say that the rate of heat generation is equal to the change in temperature across all resistors divided by that total resistance. And again, since we have the silicon carbide layer on both sides, we have to multiply this entire quantity by 2 because we have heat going through the top silicon carbide layer and through the bottom. And so then if we go through and substitute in our total resistance expression and plug in some of the numbers, we get that the maximum rate of heat generation must be no greater than about 1.3 milliwatts. So that part of the problem wasn't too difficult. It was pretty straightforward. It's just a simple thermal circuit and then just plugging in some values. So this was the easy part. Now, if we consider the system with fins, we have to do some extra thinking. So we have the total resistance in this case being equal to the conductivity thermal resistance plus the thermal resistance that's associated with the fins. And that fin total resistance is composed of a convection thermal resistance that occurs at the base of the fins or the surface of the silicon carbide layer. And then we also have the thermal resistance of the fins themselves. And so since those two resistances are in parallel, we have to add them as such. And so looking at the thermal resistance for the convection occurring at the base of the fins separately, we can say that the base convection thermal resistance is equal to 1 over the convection coefficient times the area of the base. And this area of the base is not the same as the area that we used in the first part of the problem, because now we have a bunch of fins that detract from that total area experiencing the convection heat transfer. So to account for that area loss, we have to subtract the total area that the fins take up. And so we have the area of the base, the total area, which we're given actually, minus pi r squared, the cross-sectional area of each fin, assuming that they're cylinders, times the number of fins. And so when we plug in those values, we get that the area of the base with the fins is a very small number here. And so that's part of our equation. We have now this part right here. And so now we need to look at the thermal resistance of the fins themselves. And this is where things get a little bit more complicated. And we have to use those assumptions that we made. So looking at the fins, the heat transfer through the fins, we can use the governing equation that we listed before. And again, we can say that the thermal resistance due to the fins is equal to this expression, which we had mentioned before. And so going through each of these unknowns, we don't know the efficiency of the fins, and we don't know the area that the fins take up. We do know the number of fins, and we have the convection coefficient. So it's just these two terms right here that need to be derived. And so if we want to find the efficiency of the fins, we have to take the heat transfer occurring through the fins, or sorry, the rate of heat transfer occurring through the fins, and divide that by the maximum possible rate of heat transfer occurring through the fins. For the actual rate of heat transfer occurring through the fins, we can go to table 3.4 and look at case B in the textbook. And it'll give us this expression right here, this capital M times the hyperbolic tangent of this lowercase m times the characteristic length. And this is a special case for the adiabatic tip assumption, the adiabatic tip case that we're looking at. And then the maximum possible heat transfer rate is equal to the convection coefficient times the perimeter of the cross-sectional area of the fins times the characteristic length times this theta b term. And so now we can do some rearranging and some substitution to be able to simplify this down to a more usable equation for our fin efficiency. And so looking again at table 3.4, we can see that the capital M term is equal to this square root of the convection coefficient times the perimeter times the thermal conductivity times the cross-sectional area times outside of the outside of the square root times the theta b term. And so you can see the theta b term cancels out in both the numerator and the denominator. And so if we do a little bit of math magic and we say that h is equal to the square root of h squared, and the same for p, we can rewrite this expression as this term right here with everything under the square root. And then you can see that there are some variables in the numerator that can cancel out variables in the denominator. And we'll get to that later. And then all of that is multiplied by the hyperbolic tangent of this lowercase m times the characteristic length all over the characteristic length. So if we do that simplification that I was just talking about, we can see that this term is equal to 1 over lowercase m. Again, that is an expression given near the table. So our final expression for the fin efficiency is equal to the hyperbolic tangent of lowercase m times the characteristic length all over that term. So m times the characteristic length. So what is the characteristic length? Well, I mentioned before that it's a way to determine the scale of the system. So it's comprised of the dimensions that are most important for determining the scale. And from our governing equation list, we can see that the characteristic length is about equal to the length of the fins plus 1/4 their diameter. Plugging in all those numbers, and we get this small number for the characteristic length, which makes sense. Again, we can solve for m using this expression given near the tables. It's probably also written somewhere in your notes. And going through and simplifying some terms after plugging some expressions in, for example, the cross-sectional area is equal to pi times the radius of the fin squared, and the perimeter of the cross-section is equal to pi, 2 times pi times the fin diameter divided by 2. So you can see how things start to cancel out, and we're left with this final expression. And we obtain a very large number for lowercase m. So now we have everything we need for solving for our fin efficiency. If we take the hyperbolic tangent of m times the characteristic length and then divide that by m times the characteristic length, we get something like 0.99814 or 99.8% for our fin efficiency, which is quite high, but that's okay. We have been making some estimations here, and so any calculation that we do by hand is likely going to be a little bit off of what it is in reality. But that's okay. We can get some boundaries or some minimum and maximum boundaries by doing these hand calculations. Um, so looking then at the final term that we need to solve for our fin thermal resistance, the area of the fins. This is about equal to the perimeter of the fins times the characteristic length. That was given in our governing equations list. And we get this very small number for the fin area. So then plugging everything we have into the fin thermal resistance equation gives us this. We're left with 17,483.8 Kelvin per watt for our fin thermal resistance. So that's great. That's pretty much all we need. If I go back a few slides, you can see that our R total is equal to this conduction thermal resistance plus 1 over the base convection thermal resistance plus 1 over the fin thermal resistance. So now we have everything we need to solve for the total thermal resistance. And then if we have the total thermal resistance, we can then solve for the maximum rate of heat generation. And so if we go ahead and do that, we can plug in all the numbers that we just solved for, that we just calculated. The conduction thermal resistance is going to be exactly the same as it was for the first part without the fins, because that thermal resistance just goes through the silicon carbide layer that's surrounding the computer chip. Sorry, I guess it's not exactly a computer chip. It's just a little case of small electronics. But again, we have to multiply this whole expression by 2 because we have heat transfer going through both the top and the bottom. And we're left with our maximum heat generation rate to achieve or to maintain the chip temperature less than 85 degrees Celsius. So this maximum rate of heat generation is equal to about 8.6 milliwatts. And so that's how you solve problem 3.115. Let's go back and see what's different between this solution and maybe the solution that's given. I mentioned before that my thermal conductivity is lower than the thermal conductivity that I saw when I took heat transfer 1 and did this problem. But you can see that the numbers that I'm getting are pretty much exactly the same as they are if you use a thermal conductivity of 490, I believe it was. And so what that tells you is that the thermal resistance due to the fins is likely not contributing too much to the total rate of heat transfer. And so a lot of it is coming from the convection occurring either at the surface of the unfinned chip or on the fins themselves, if you do include fins. And so another thing to note is that the maximum heat generation rate for the fin case is about 8 times, a little bit less than 8 times greater than the maximum heat generation that's allowed for the case without fins. And this makes sense because the whole point of fins is to draw more heat away from the chip. And so if the fins are drawing more heat away from the chip, that means that it can generate more heat and still maintain that 85 degrees Celsius temperature. So that's how you go through and solve problem 3.115. Thank you.